on today's Institute lecture, a very special lecture that we are having on the occasion of National Engineers Day. And we are very fortunate to have somebody as distinguished as Professor Tarun Kant, who will be delivering today's lecture. So today's lecture is being organized jointly by IIT Delhi as part of its Institute lecture series, and also INSA, which is honoring Professor Tarun Kant today, and we'll go over the details of that in a little while. So it is my pleasant duty to welcome everybody here for the Institute lecture, and in particular Professor Tarun Kant, who is a speaker for the day. So as we know, today's lecture is also commemorating the National Engineers Day, which is the birthday of Mr. M. Visheshwaraya, and therefore a real milestone, particularly in terms of civil engineering. And who better to talk about a theme central to civil engineering than Professor Tarun Kant. So with those initial remarks, I would now hand over to our Deputy Director, Professor Ashok Ganguly, for his welcoming remarks, and then we'll continue with the proceedings for the afternoon. Professor Ganguly.
Good afternoon, everybody. It's a privilege and an honor for me to be part of the Engineers Day special lecture. Especially, it is more special that the INSA, the medal on this day, is being conferred upon Professor Tarun Kant of IIT Bombay, and it is on Brahm Prakash medal, and I believe Brahm Prakash was in Institute of Science in materials department, metallurgy department, and so it's a great honor that such a great we are celebrating Dr. Vishweshwaraya's birthday at IIT Delhi. And even more important, that INSA has chosen IIT Delhi for this award to be delivered today here to Professor Tarun Kant from IIT Bombay, who is a colleague of our director, Professor Ram Gopal Rao, comes from the same institution. So that's again another connect that we have. So thank you, Professor Tarun Kant, for coming to IIT Delhi, and for INSA for choosing IIT Delhi for this award. Thank you very much.
Thank you. So we'll continue with the proceedings for the afternoon. So the next thing on the agenda is the lecture by our distinguished speaker today, Professor Tarun Kant. So to moderate the lecture and also following that the question answer session, it's my pleasure to invite my colleague, Professor Vasant Matsagar of the Civil Engineering Department. So Vasant, over to you.
Thank you, Professor Roy. Good afternoon, everyone, and happy Engineers Day to one and all. I would like to once again welcome you all to this 2019 Professor Brahma Prakash Memorial Lecture, as well as IIT Delhi Institute Lecture. It is my honor to brief you some of the distinguished accolades of Professor Tarun Kant. So Professor Tarun Kant is presently a Professor Emeritus at IIT Bombay. It is an honor which is bestowed only on few select retired faculty members. Through an endowment of rupees 1.15 crore created by his students and well-wishers in the industry, Professor Tarun Kant Endowed Chair was established in his honor in the Department of Civil Engineering at IIT Bombay on 19th March 2020. His CV runs several pages. However, I tried to take some abstract out of it, and with due permission of everybody, I am reading it through some of the highlights of his research contributions, particularly in the mechanics area. Professor Tarun Kant was elected as a Fellow of Indian National Academy of Engineering in 1999, a Fellow of Indian Academy of Sciences IISc in 2004, a Fellow of Indian National Science Academy in 2007, and Fellow of National Academy of Sciences in India, NASI, in 2011. Notably, he is the first civil engineering academic in the country to get elected to all the 4 national academies. Professor Kant was a visiting scholar at University of Wales in Swansea during 1979 to 82. And he was also a visiting professor at the University of Cambridge in UK during 1993 and University of California in Los Angeles in 2005. Some of the major awards that were bestowed upon him include 1979 Jawaharlal Nehru Memorial Trust UK Fellowship, European Commission Senior Faculty Exchange Fellowship, Professor H.H. Mathur Award for Excellence in Research in Applied Sciences, Khosla National Award for Lifetime Achievement in 2010, IIT Bombay Research Paper Award, Lifetime Achievement Award of IIT Bombay, Legends and Pioneers in Mechanics of Composites by the APACM, Senior Scientist Award again by the same organization, Lifetime Achievement Award by BITS Pilani, as well as now the INSA Professor Brahma Prakash Memorial Medal. And also in 2020, he is bestowed upon with the Wasik Award. He has published 160 research papers in referee journals, 6 chapters in edited books, and about 182 papers in conference proceedings, and edited 4 books, and he serves on editorial boards of 5 international journals. He has supervised 27 PhD candidates, over 78 masters, and over 90 BTech students. He has also been a referee for over 100 external PhD theses. He has research and citation standing in terms of H-index of 45 on Google Scholar, 35 on Web of Science, and 40 in Scopus. His current citations are over 7,923 on Google Scholar, over 4,082 in Web of Science, and 5,113 on Scopus. He is in the top 0.365 in the list of top 2% global scientists. His sustained efforts over 10 years resulted in establishment of Interdisciplinary Research Center for Computational Engineering and Science at IIT Bombay since the year 2018, with generous funding from the Department of Atomic Energy, Government of India. He was elected president of the Indian Society of Theoretical and Applied Mechanics for 2 terms, 1999 and 2000, has founded 2 associations. One is Indian Association for Computational Mechanics in ACM and Indian Association for Structural Engineering ISE, and is responsible for organizing the biennial ICCMS in International Congress on Computational Mechanics and Simulation and Structural Engineering Convention congresses in the country very successfully. The president of one of those associations is again with us, Professor Santosh Kapuria from Applied Mechanics Department at IIT Delhi. Besides his scholarly and notable scientific contributions, he has displayed leadership initiative and has made long and sustained contributions in the field for over 50 years and recognized as the face of India in computational mechanics. He is also responsible for convincing a donor of Mr. Jitendra Mehta, a 1963 alumnus and successful civil contractor in California, for creation of the first endowed chair in department, the JK and MJ Mehta chair. He also mobilized more than 1.15 crore through small donations and contributions to alumni, friends in the industry, and his own personal funds for creation of unique endowment chair in the department. Only and the first Indian academic scientist to have been invited to give a plenary talk at the world-famous WCCM EPICOM during 2016 in Seoul, South Korea International Computational Mechanics Conference. So we are indeed fortunate to have Professor Tarun Kant delivering his lecture today on the evolution of micromechanics of laminated composites. We would, of course, like to hear more about this from Professor Kant. So I would hand it over to Professor Tarun Kant to deliver his institute lecture as well as 2019 Professor Brahma Prakash Memorial Award of INSA. Professor Tarun Kant, please.
So thank you very much, Vasant, for a very elaborate introduction. And I'm indeed fortunate and very happy to to be present today on this occasion of Engineers Day, which is celebrated throughout the country as Engineers Day, to commemorate the the birthday of one of our finest engineers that we have produced, finest civil engineer that we have produced, I mean, he was, in those days, Visheswaraya, Mr. Visheswaraya was extraordinary engineer, a field engineer who has done so much for the country. His lifestyle is sketch is very interesting because he joined Bombay Municipal Corporation as an engineer. Now you can imagine a person of Bombay Municipal Corporation thinking about the country and doing so many things about. He devised the underground sewerage system for the old Bombay, which is still functional. And so there are so many. And then I'm also thankful to IIT Delhi for asking me to give this institute lecture. So this is another, and of course we are also having this lecture along with the memorial lecture of Professor Brahma Prakash. Now, Professor Brahma Prakash memorial lecture, you are not going to show his.
I will show when the medals will be present.
Acha, when the medals will be present. But anyway, I will give a small sketch of Professor Brahma Prakash. He again has a very interesting person. I mean, he got his PhD from MIT in material science and metallurgy. In those days, it was metallurgical engineering. And then he came back to India and joined IISc, became a professor very soon. In those days, of course, professors, I mean, he was from MIT. So he became professor and head of department, served there for about 3 years. And you see, he moved to atomic energy as a head of metallurgy division. Now, this is very interesting. Normally, no academic person would, who is occupying a professorial position in IISc or IIT would normally move as head of a division only. In those days, it was a division. So, but then at the advice, at the insistence of Dr. Bhabha, because he wanted a materials man in atomic energy. And so Dr. Brahma Prakash, he moved to materials, he's the first metallurgist to join that division and became its head and did so many, innovations in the early years of atomic energy establishment. So I'm really honored to give this talk today on the occasion of so many, so many people who have been who have contributed to the growth of this country. Now, my talk is I have been a student of solid mechanics. Solid mechanics, it is a very classic subject. It has a history of over 405 years. Yes, it is a. I'll just take up but let me tell you, it has a history of over 500 years. Both solid mechanics as well as fluid mechanics. So it is not that the subject has developed over last these 500, so many years, and I have made very little contribution in the last, say, 35 years or so. And I would like to give a précis of that in a, I have avoided mathematical description of the subject. So it will be a kind of historical description of how the subject has developed over the last about 50 years. And so this is my evolution of micromechanics of composite laminates. Nobody knew about composite laminates until about 1960. It was not known. Every material was only a isotropic material. See, material. All the mechanical engineers are metallurgists. They were all, dealing with materials which was. So this is, but then composites have already come in technological field. See, we feel as engineers and scientists that we are doing a great job. but technology always is ahead of us. Even without the mechanics, they were, it was, composites were used. Composites means, combination of more than two materials and to give a better performance. So it was used in World War II in the defense equipments. And that time there was no mechanics, but it was there, But only thing is what what is the use of mechanics is that if you know the mechanics, if you know the how to analyze, how to know the state of stress and strain in the body, then you get a kind of confidence in you. That was not there because earlier it was based upon only empiricism. So now we can, it is, we know that what we are doing, and we also can see that, yes, these systems that we are designing, they are withstanding the environmental loads that they are subjected to. And our theories are, yes, they are doing the job. So this is what the confidence that we get, which was not there earlier. But this has happened, so technology always precedes the analysis. And this must be kept. So, and same thing has happened in aircraft. Aircraft engineer, it's not that, before the aircraft analysis started, the aircraft were not built. They were built based upon experience. So, page down, okay. Okay, so this slide I always show for, to acknowledge. I mean, I joined IIT Bombay in January 1971, and to be precise, on 20th January 1971. And I have remained there only throughout, from that day onwards, and I'm still there. So it is over 50 years that I have been there. So I'm grateful to the IIT Bombay for providing me the environment to do a little, make a difference to the society. And then the next organization that I would like to thank is Department of Science and Technology. See, in those days, funding was a problem in early 70s. So I was fortunate in getting some funding from DST in my early career. When I was even a lecturer, I got some two projects from DST to do something. And that gave me some motivation. See, it helps you to, it motivates you. That is all. It is not that you are doing something something extraordinary, but yes, it motivates you to do something, and it helps you to grow. And same thing happened with Aeronautics Research and Development Board of Ministry of. They also supported my research and continuously. Then the third organization is the BRNS, Board of Research in Nuclear Sciences, Department of Atomic Energy. So these three organizations I would like to acknowledge. And plus, the most important and most is we are nothing. We professors or teachers are nothing without our students. It is they who work, on the ideas that you give them, and they bring the results, and then you try to do something, and present it to the world. So this is all, and there are many students, but at least some of them who have directly contributed to the subject of mechanics of composites are the following. I have just listed them up to the latest being the Devesh Punera, who has become assistant professor in IIT Bhubaneswar, and he's doing well, very bright chap. Another bright chap is in my list of course, all of them are extra, but then extraordinary, is I will say Mallikarjuna, yes, 1991 PhD. No, he's Manjunatha. Mallikarjuna should be before. Yes, 1989. Yes, Mallikarjuna. Yes, I think he has a single name. There is no other single word is there. Mallikarjuna. Now after going to USA, he has added Benur. He has changed his name and made it Benur. Mallikarjuna Benur. So okay, so but they have all contributed enormously, and so this is. And then, so I dedicate this lecture to all my former students, and because we are nothing without them. it is. So I just now said that, yes, this subject of mechanics, and specifically the solid mechanics, has a very long history. So if you start seeing the the historical books like Timoshenko, history of strength of material, and Todd Hunter's book on history of theory of elasticity, and so on and so forth, which were written, around 1940, you will find that, these are the timeline I have given. But let us say we start with the first one. Leonardo Vinci, a 1452, because these people are responsible for, development of the humanity. See, without civil engineers or structural engineer or solid mechanicians, you cannot have buildings, you cannot have structures, you cannot have, habitats, you cannot have roads, you cannot have drainage, you cannot, so these are the people. He was a great architect and, and constructor. So you can see from 1400. So it's more than you have the next person I have put is Galileo. Yes, he gave us. He also did a lot of to the mechanics of solids. Great contributor. Hooke's law. From 1635 to 1703. You can see. So we all know Hooke's law. What is Hooke's law? So he's a great contributor. Then you have Bernoulli. Now the Bernoulli is a big family. They are great people. Not only one Bernoulli. There are, I think, 3 or 4 brothers, Swiss mathematicians, and all were extraordinary mathematicians, one after another. So Jacob Bernoulli is especially responsible for giving, starting the beam theory. Beam theory was started much earlier, even in, it is started with Da Vinci also tried to do something about the beam analysis, simple beam analysis. That is what we see in a structural member, in a building. So how to analyze, how to find out the state of stress in a beam. So this is Bernoulli. Then we will have this is his brother, John Bernoulli. He was another contributor to both mechanics of solids as well as fluid mechanics. And then we have Euler. You see, there is a classic beam theory, a one-dimensional member subjected to transverse load, the behavior of that under the load. That is, how to go about analyzing, how to go about finding the state of stress inside that was done by Bernoulli and Euler. So still we know Bernoulli-Euler beam theory. So these were the great contributors to this subject. Then we have Young's modulus. Thomas Young. Then this is Poisson's ratio. Poisson's we all call, Poisson's ratio. If a material is extends in one direction, there is shortening in other direction. So there is the strain in transverse direction to longitudinal direction. The ratio of the two strains is given by Poisson. So they are all great contributors to this mechanics of solids, and we are just continuing the same subject, trying to take it further. Then Navier was a French mechanical engineer, and then he gave, of course, he gave the famous Navier-Stokes equation, but he also contributed to solid mechanics. We have Saint-Venant. Again, Saint-Venant's principle we use in theory of velocity, day in and day out, Saint-Venant. Then Kirchhoff, G.R. Kirchhoff, Gustav. Now, responsible for theory of plates. He contributed to, but before that, the plate theory was started by another gentleman, that is Poisson, which I have already explained. So Poisson developed the plate theory. Plate theory is a two-dimensional member, and the thickness is very small, and it is transversely loaded, supported on all edges. So the theory was devised by, because once you have one-dimensional beam, so you have to graduate from one-dimensional to two-dimensional. So two-dimensional it became a plate. How does a slab of a building is nothing but a plate? How does it behave under the action of load? Can we find out the state of stress within? So this was started by Poisson, and but then there was some issue regarding the boundary condition satisfaction for free edges, and that was resolved by Kirchhoff. So now we call it Poisson-Kirchhoff plate theory. Many people forget about Poisson and they say only Kirchhoff theory. I think we should contribute. We should give contribution. I mean, we should acknowledge the contribution of everybody who has contributed to the theory. So this is now let us come closer to this. This now we have come to the modern era. Stefan Timoshenko. He is the father of solid mechanics. Father, we always say, I've written here, father of modern engineering mechanics. An Ukraine born, and after First World War, he ran from there, came to which is the Muslim, which is the great. Huh? No. That was later. But first he served in Europe. In I'm forgetting the country. Huh? No. He was not in Germany. Anyway, so he was. He came. And then finally he settled down in Stanford University, where he did most of his work. But his work had started way back, in Soviet Union before that. And he is the one who wrote most of the books on solid mechanics in English language. So he is contributed, because normally as teachers, we start teaching a subject when there is some material, available. And this person gave all the books that are there now for us to teach. So first set of books were given by Timoshenko. There are no books before that in English language, not even British. So it was only Timoshenko that, but when I go to these colleges these days for MBA accreditation, of course, now I have stopped. They are also not calling me, MBA. So, but then I used to ask them, have you heard students, third year students, second year, have you heard about Timoshenko? No, sir. What have you heard, sir? We have heard about Wazirani Ratwani. That is the book you followed. So this is how, so the teachers also do not know, and students also are not being told, the history, who is the contributor. So it is very sad state of affairs in the country, that the quality of education that is going on, especially in the private institutions, is far from satisfactory. So they simply don't know, what they are studying, because there are made easy books that are available in the market, and they teach, they learn, they teach, and not only they, but their teachers also have learned from only those books. So they also don't know. So this is the status. Okay, so I think I have given enough of, there is another person, because Timoshenko is, for us, he is very famous, and he has done so much for the subject. But there are other, because there is also Timoshenko beam theory, which was devised by Timoshenko. But now, very recently, it has come to light that there was another person who contributed to that beam theory, and he happens to be, his name is Ehrenfest. Paul, historical. So he's a Austrian Dutch, theoretician who contributed, who collaborated with Timoshenko, and that Timoshenko beam theory should be called Timoshenko-Ehrenfest beam theory. I mean, this is what if both of them have worked on the same, somehow we forgot to mention his, so this is also, I found out that this is, okay, now, yes. Another person who is very famous in our subject is Mindlin. He is a mechanical engineer, American, and he contributed, in fact, his contribution is that to this, especially this subject of composites, because nobody knew about composites until, as I told you, 1960, 1959. Things were all isotropic. So Mindlin had not worked on composites, but he worked on only isotopic material. But then he had gone a step further and did something which were found later on to be useful for composites. That is all. It was much later it was realized that yes, whatever he had worked is useful for the material that now we have got. So that way it is important. Eric Reisner, another great person whom we must know, and he was a professor in California, and basically a German, and he has contributed again to the subject of that I'm going to discuss today. And he developed what is called Reisner's shear deformation plate theory and shell theory, and also some variational principles. Those are have become extremely important. So Reisner is another. So this is a brief historical history of our mechanics, the people who have contributed. So basically, what I'm going to say, talk today is about simple things, very simple. First of all, I do not know much. My knowledge about the subject is very little. I know only linear mechanics. People work in non-linear hypermaterial, and so on and so forth. I don't know it. I have stopped with linear mechanics. Okay. Then I don't know tensor mechanics. I don't know tensor theory. I use normally the longhand, matrix methods, matrices in order to express the equations, because I found it more convenient. I have never been able to grasp the subject of tensor, but tensors have become very important, I think, if you want to generalize the theory for nonlinear. So basically, the material, the type of material, they are listed on the left. You have isotropic material. You have because it is a material which are very important for. So these beams, plates, shells, they are they are very important components of our structural engineering, solid mechanics. They are very, very important. They are used, they have been used everywhere. Shell is a curved plate. All the roofs of churches, temples, then mosques, what you find, the roofs are the bigger stadia. We give a shape. The idea is to have a larger area without columns, without any obstruction. So how to construct? So, and the mechanics of that is, so I will say, so it started this isotropic material, then orthotropic. Ortho, as the name indicates, the material properties are different in the orthogonal, three orthogonal direction. Then came laminates, materials which are layered material. You keep one layer of material, then you put another layer of material which can be isotropic or orthotropic, again third layer, fourth layer, and then you make a new material, a new laminate. Now, new thickness. Now, there is a difference between each layer. Each layer we call it, and so now, then we also have sandwiches, just like we eat every day in our morning breakfast sandwiches. So we can also have two stiff layers sandwich, which is sandwich. One very material which is very soft is sandwich between two stiff layer, and then you make use of this element for your system, for your structure. So that is a sandwich structure. Then piezoelectric material which are dependent on electric current. By changing the electric current, you can change the shape and of those, structural element. Now the new material has come functionally graded. You can design a material by prescribing the form of the material. Form, how does the material property change in at least one direction? Forget about in all direction. Of course, people are thinking about all direction, but at least in one direction, it is very easily done. In one direction, I can change the material properties as per our requirement. Now, this is a functioning FGMs. And of course, when it comes to analysis, we have static analysis, or then free vibration we normally do. Then we find out the buckling analysis. What is the total carrying capacity of the system? Then we do dynamic analysis. We do also these materials change with under action of thermal loads, thermal analysis. So these are the types of analysis that we do with the kind of structures which are made of these on the left hand side, these materials. So it is a complex. Isotropic was a simple because a property which is independent of direction. Every point has the same property in all the direction. Now that was isotropic. So at any point, if the properties are same in all the direction, we have isotropic. So that was the simplest material that we had got. Now the first paper, I think it should be, sorry. So composite, of course, I have already talked about composites, but basically just to give you, it is a combination of material wherein each retains its individual identity while contributing to an, improved behavior. So there are so many materials which are joined together, and the total material is, gives you a improved behavior. Now, fiber reinforced composite, that means if fibers having high specific stiffness, very strength, high strength, and stiffness and strength, and these fibers are made of glass, carbon, graphite, and so on and so forth. There are so many, they are very, very strong. They are embedded in a matrix material. They are embedded in a matrix material, which is polymeric in nature. It can also be ceramic. It can also be metal. You can always do, strong fibers in metals also. That also can be. So if such materials are there, so that is what is fiber reinforced composite. It need not be polymer, because we started with polymer, but now people have started carbon, metallic, and so on and so forth. I think I will skip this. These are the applications. This is how they become. So single layer of this material, single layer, we call it a ply or a lamina, a single sheet. I think single sheet of the material, a single page, this page which can be isotropic, it can be orthotropic, means you can have some fibers in one embedded in one direction. So single sheet is called a lamina or a ply. And once you join, if you put number of layers one above the other and join them together, we call it laminate. And that is how the construction goes. I mean, here it is on the left-hand side, it's very clear how the material looks. The first one, macro, which you can see with your eyes. So, but now nano, you see, you can go to the smaller scale and micro level. So, of course, material scientists, they also deal with, but we are all engineers, we have, but now engineers are becoming scientists. So they are turning to material. You see, this is another, for the last 20 years, I'm finding now people have forgotten about their real structure, real system that they see in front of them. They are going more towards the so smaller nano, and trying to do so many things, and many things have come, has been done unnecessarily, without making any impact, without any like utilization of Newtonian mechanics for a problem at nano scale. This itself, physically, it is wrong. It is not. I mean, unless you go to quantum mechanics. what people have been doing, and getting the results. But I do not know what value they have got. But yes, it is going on. So before, I think I missed one slide. I just 1 minute. Let me just check up. I wanted to, where is this? I said that the first book or first, no, I'm sorry. Somewhere it is there. How come I missed? First book. Okay. So this is what, yes, it's here. So I have been telling you, that until this is the first paper, by the way. It is always the paper. Importance of a paper is there, a good paper in a good journal is there. And which we must realize, our students must realize that it is not just doing a PhD or a master's thesis and getting the thesis, stacked in the library. Nobody will know about what you have done unless you publish it. So your material should be publishable, and it should go outside your institute. So this is the value of that. And then it is archival in nature. You should be able to see it even after 100 years. So this is the first paper that appeared in 1959, and using Poisson-Kirchhoff theory, Poisson-Kirchhoff plate theory for analysis of a layered plate. It appeared in ASC Journal of Engineering Mechanics in 1959, which is a very reputed journal in our civil engineering in mechanics. So, and the first book I have already told you, first book English language is Timoshenko and Krieger, and Theory of Plates and Shells. And the English edition, actually, it is the first edition was in 1934, but nowadays the one which we are using is 1959. Okay, so this is, so how to go about analyzing. So first was Poisson-Kirchhoff. I told you that Poisson-Kirchhoff, this first paper appeared, and well, for a layered material, and we got people, the K.S. Pister and Dong, the two authors, which is shown there, Pister and Dong, S.B. Dong and K.S. Pister, they got some new result for this material. But then there was nothing to cross-check or validate their results, So, and why did they use this theory for analyzing this? See, this theory was okay, Poisson-Kirchhoff theory, okay for isotropic material. Now, normally for such material, you don't have what is called shear deformation, or shear energy is not there. There are different kinds of energy that exist inside the body when it deforms. So the shear energy is not there for isotropic material. But once you have a composite, once you have a shear deformable material, which is composite, then the shear energy becomes important. But then this theory did not have shear energy, but still they used it because it was available in this next book. Book theory was available, so let us apply it to a new material. This must have been their idea, in those days. And they got the result. Now, but then there was nothing to prove, and things became, how to validate. And just now I told you that these are some assumptions that are used in, because I will not go through it in detail, but these are the assumptions that are used in Poisson-Kirchhoff theory. One is transverse shear deformation, that is, they are neglected. And we assume that this is in thickness direction. The transverse normal remain straight and normal to the mid plane. Normal, this 90 degree is maintained here. So after deformation, this line and this axis, this longitudinal axis, the normality is maintained. So that means there is no shear angle. So shear energy is 0. And they also assume the thickness of the plate does not change during deformation. So thickness of the plate does not change during deformation. And thickness, this thickness, because plate has some finite thickness, this does not change. So that means there is no transverse normal strain. This is zero. And most of the theories until very recently, this was the assumption, even after the improvement, that this strain is always taken to be zero. But which is, one should be wary of this. One should realize that what is the problem? A composite material, which is material is a little flexible, and once you apply load, the thickness will change. And therefore, this assumption was not the right one. And of course, there are something that we make use of to simplify the Hooke's law. Okay, so after the first paper, number of papers came suddenly, and that is what happens. One paper after, so that triggered so many people to work on the plate, and then they produced, but still for different types. One was that was simply, now here it is a the Dong, same Dong and Pister and Taylor, they did it for cells, because they had done it for plates, but again they did it for cells as well as, and then did it. And so there are many papers that came in the 60, from 60 to 69, based upon this theory. But this theory had limitation that, of course, I just said that transverse shear deformable, this was neglected. And nowadays we realize that this theory, I think around the same time, finite element, see, in 1960, the composite started, and around the same time, computation also started, numerical methods, because of the advent of digital computers. So another method that got invented was the finite element method, and finite element method also is was developed by no other than civil engineers. It was developed by civil engineers, and which is now used as a black box by all the engineers throughout the world. But if you see in early 1960, it was developed by a couple of civil engineers who came together to design an aircraft wing. So because civil engineers have a good background of stress analysis, better than mechanical engineers, I must say that. So this is important, because our curriculum emphasizes this analysis much more than what it is done in mechanical, because mechanical engineering is yes. So I mean, I have no. So this is a fact, I mean, he cannot refute this, You may, I mean, somebody may. So this is, but then. So a good civil engineer is better equipped to analyze a system, is a solid system, than a mechanical engineer. So the numerical method, which was invented by in 1960 by was again a civil engineer, and we must take pride. Civil engineers must take pride in giving of the 20th century a method that is universally now used by everybody. I mean, physics, chemistry, mathematics, material scientists, everybody talks about finite element without knowing who were the inventors. Okay, so these are some limitations and of the theory that existed then. I think I must check my time, and we started around 3:30. So I should, yes. So yes, so it is 4 o'clock. So I must be. Okay. So soon it was realized, although number of results came, but then soon it was realized that well, we have to do something better. Transverse energy, shear energy must be considered even if you don't consider the normal energy, the change in the thickness of the laminate, change in the thickness of the plate or shell or a beam. If you don't take even that consideration, then you must take at least shear energy. Shear energy is very important. So need for shear deformable theory that started how to take shear energy into consideration and develop a theory which can predict the behavior of these structures. So that became, and so then Reisner's theory, Reisner way back in, this is now I'm talking of 1960s. Way back in 1943, Reisner had done a paper, 1943. He had written a paper in Journal of Applied Mechanics, which is again a very reputed journal, but that is, and gave a theory which included shear energy, but it was lying in that journal. Hardly anybody, 1943 to 1960, 65, 69, nobody had ever used that or taken note of that. And similarly, in 1951, Mindlin had also given a slightly, because Reisner's work was on stress-based and Mindlin's work was on displacement-based. These are two different approaches to arrive at the same solution. So Mindlin in 51 had done a similar work, and it was there but for isotopic material. Then somebody must have seen, oh, this is already there. Why should we use Timoshenko book? Why not take these papers? So Timoshenko book was, now people said, oh, let us go away from Timoshenko's book, whatever is given. Let us use this and develop a theory. So that theory, the only thing that did was that we included this transverse normal, which was 90 degree from longitudinal axis to transverse. This 90 degree, after deformation, this theory is assumed that this remains straight, but not necessarily normal. Not necessarily normal to this angle is no more 90 degrees. Between yellow line and this dotted line is no more. So there is shear angle here. So shear energy was included. All other assumptions remained the same. So it incorporated the effect of shear deformation into, and and then the work is started. So this we got a second set of people who started working on this, and some papers came. So this is what I was saying, 1945. Reisner did his work in 1945, Mindlin in 1951. And then applying these two, in 1970, Whitney and Pagano, they came out with a paper here, which for anisotropic plate. And Dong was already doing work on this, so he also used this. And recently also, there are a number of papers that came using these. So this is how, so now we have two. The second one is called, it is an improved theory. So it is not classical lamination theory, but we call it first order shear deformation theory or shear theory. So CLT and FOST, now two sets of results were available for people to see, but still there was no benchmark solution. After all, what is the actual value? What should be the benchmark solution for such problems? Because still it has some assumption. So so this was the status at that time. But anyway, two sets of results were there, and there were some differences that were found, and they were not able to bridge the differences. So then, then came need for how to solve this problem. Why do you make assumptions? Then it came, why can we solve this problem of 3 dimension? Any body is a 3-dimensional body. However small it may be, however small the thickness of the plate may be, it is a 3-dimensional body. So can we analyze this plate without making any assumption, using what we call our classical theory of velocity? So theory of velocity gives you the exact equations of any solid. Can we analyze for this plate, for this rectangular type of plate, can we solve this without any assumption? Now, that was the status at 1970, and it was in US, Pagano, by name NG, Nick Pagano, is NJ Pagano. And around the same times, here in India, in ISC Bangalore, there was a PhD student, Srinivas, a student of A.K. Rao. Professor A.K. Rao was in aerospace engineering. So he had given him, A.K. Rao told him, okay, you solve a plate without making any assumption. Because there are already Timoshenko book is there, and then Reisner theory is there, but I don't want any assumption. You try to solve this problem without making any assumption. So that was a challenge, and it was very difficult. And that too, he asked him, you were to, finite element had started, but he said, no, don't use finite element, you do it analytically by mathematics. He could produce. So Srinivas did a great job, and same thing Pagano. But now the surprising, what I would like to say is, see, Pagano, if you see the three-dimensional solution, so third set of solutions started coming, and that, 69, Pagano, first paper came, 3D, but anyway, simplified. It was only, actually, it was a 2D problem, simple 3D problem. So it is called, we say, cylindrical bending. In 1970, it's a bidirectional, 1970. And Srinivas and A.K. Rao also 1970. You see, what is most important, around the same time, both, now this paper of A.K. Srinivas this journal is more reputed. This journal is, International Journal of Solids and Structures, than this journal, Composite Journal of Composite Material. But unfortunately, even our Indian students don't refer this Srinivas and A.K. Rao even today, and they prefer to refer only, it is mindset. So that must change. I always, whenever I talk to my students, and I tell them, you must respect everybody equal, why do you think that Indians are inferior? At least we are second to none in this area, let me tell you, even today. We, in this mechanics of composites, we are second to none anywhere. We are all, in the same at the same level. So why do you think that by referring your own your colleague or your own Indian friend, you are you are doing a disservice. So this is a very, so as a teachers also we must emphasize this, that this is and this is happening. As it is, we don't get citations. See, Americans don't refer our papers. This is also there. There is apartheid, this is also 100%. And then our own people, if they don't refer our papers, then where will we? What will we do? So this is a very sad state of affairs. So now we had 3 sets of results, and this was the last one, was a benchmark solution without any assumption. So we could at least see, what are the regions, and yes, where the earlier two solutions stood, and things like that. So this is, I will just say, I will go a little fast. So this was the first part of I wanted to give you the history of how does mechanics has progressed in the first 10 years. First 10 years of its existence, composite, when the non-isotropic mechanics is started. And then, of course, but then you cannot solve three-dimensional problem for everything. It is difficult problem. 3D as such is a very tedious problem. So you can do it for one or two simple situations, but you cannot solve for realistic problem, 3D. So therefore, the need for a if you can reduce somehow the dimension of the problem to 2, and then because the first 2, the Kirchhoff plate, Poisson-Kirchhoff plate theory, and the Love shell theory, and same thing for the Reisner plate theory, the thing became 2-dimensional. So it was a 2-dimensional analysis of a 3-dimensional body. And then we have solved a three-dimensional problem as it is. But three-dimensional was a difficult problem. It was indeed a difficult problem. And we certainly cannot do it for every problem that exists in nature. So therefore, the need for a good two-dimensional formulation, which could take into account the effects of transverse shear energy and also the normal deformation, also the changes in thickness, that continued. So this is the second era, and that is started. So actually the motivation for our work is started for this, the need for how to improve the theory and get try to reduce the 3D problem to a 2D without by reducing the assumptions that have gone into the earlier theories. And I found that the first paper that I could lay I started working just by accident way back in 72, 73. And I happened to put my hands on this report, which is this is published in 1949. It was not a paper. It's not a journal paper, but it is a NACA. Earlier, it was not NASA technical note. It was a NACA, NSCA. So I could see, and then I got interested in this. When I saw this, it was there in our library, central library. So I took it and I started reading this, and I found that yes, it has got some idea, and based upon it gave a very systematic way of how to reduce the three-dimensional problem, this three-dimensional function, into a two-dimensional problem by simple Taylor series expansion. So this idea came, and that yes, we can develop better theories by taking this Taylor series expansion, and we can include both the membrane and flexural modes of deformation and develop, reduce the dimension of the problem. So this came very handy. And let me tell you, I mean, we were not behind anybody else in the world, even in those days. So it, I mean, more or less situation was same, throughout the world. So now instead of this transverse, because normally we model only this transverse normal. In the third dimension, we are modeling this transverse normal. So earlier, we have always assumed this to be straight, always remains straight, which is not the case. If it is a layered material, this will never deform into a straight line, which we have assumed. Then we only did that, okay, shear strain, we can assume that 90 degree, this angle will remain not 90 after deformation. But now it is possible to take the deformation of the normal like this. After the loads are applied, I can take this like this. So it can be totally deformed, and then I can derive all my equations with reference to only mid-plane, this dotted line. So this dimension can be subsumed, and we will get a two-dimensional theory. So this is the interesting part. And here we can include also the transverse normal deformation. Now, let me tell you, transverse normal deformation, nobody talked about it until very recently, about 10 years ago. People were so much enamored with only shear deformation, but not normal deformation. Shear deformation, but then this one was not talked about. And only our Professor Batra, Ramesh Batra. Incidentally, there are quite a few Indians who are involved in this development throughout the world. So Professor Batra, who is in Blacksburg, what is that university? Virginia Tech. Virginia Tech. He wrote a paper that inclusion of transverse normal deformation. And then he referred my paper, and that was recent, about 10 years ago. But I had used this without realizing the importance of transverse normal way back in 1982. And a good paper it was already there. So 1982 and whereas 2000. So he realized that this is very important. And then, okay, so this is the So we started the work, and I did my PhD, with Professor C.K. Ramesh, who was my supervisor. In those days, there was no research culture. There was nobody told me that you must publish your result. PhD was more than enough. Getting a thesis. But anyway, we presented something in a conference. So I show it that way back in 1976, we had done a orthotropic shells, and we presented it. And so this was our thesis. So, using all this, and we developed a theory first for thick shells, thick plates, using this. Of course, first plate was there, this, and then later on for shells. So we inserted these additional terms, and by additional terms, this improves the bending behavior. See, this is the the odd terms in the Taylor series. This is the second term of Taylor series. This is the and this is the second term. This is the fourth term of Taylor series. So cubic, all the odd terms in Z will contribute to bending behavior. And here we included also this square term in W. So that included transverse normal deformation. That means change in the thickness of the plate. And we developed it. We wrote the paper. And this was 1982 paper, which was a thick plate. And we also developed a finite element, which was the first finite element developed for this theory in the same year. So first for higher order theory, we called it higher order theory. Here I just called it thick plate. If I had known, I would have called this as a higher order, because so. But then here and when I wrote this paper, I was in Swansea. I mean, because both these papers I did it myself. And well, Zinkovich was a great man. So I showed him the draft of this paper. Professor Olek, his name was Olek. Everybody used to call him Olek, O-L-E-K. Olek, I have written a paper. Would you like to go through it? I would like to associate. Oh, why do who uses plate theory these days? You can do finite element directly, So this was his extempore reply. Why are you wasting your time in developing a plate theory? I said, anyway, I have done it. So how do you feel? Anyway, so that is how that paper came, But then attachment of a great man helps you, let me tell you. In the early stages of your career, I mean, this was seen, because of this name. This paper was seen by many great people, around the world, And I got from Belichko a letter saying that, I was a very interesting paper. I found out, and you have done this. So what I am saying, Belichko also was a great mechanician. So what I am saying, it helps in the beginning, because nobody, and this paper is more important than this, let me tell you, because this has the theory, complete derivation of the whole analysis, while this one has only a small part, only the finite element part. But then nobody refers this, but this is more. So, well, this is how life. Okay, so I will now forget. I mean, I will go a little faster. And so now we are in a different. No, we have got what is called now. The next phase is, we call it higher order theories for the behavior of these types of structures. Higher order, because we are trying to discard some of the assumptions that were made, and still we are retaining the two-dimensional nature of the formulation. This is what is the basic thing. And there is another approach around the same time. These people, Levinson, Murthy happens to be an Indian from NAL, Incidentally, he was the thesis examiner of he was my thesis examiner, PhD thesis examiner, and he had gone through my thesis very well, and given a lot of comments when he came for Viva Voce, but he liked it. And then after 1 year, he went to US under NASA fellowship. And so NASA report he wrote later, so I had done it for shells. But he made it for plates based upon, but later I told Tarun Kant, I got influenced by whatever I had seen in your thesis, and we simplified it only for plates, but then without the normal deformation, So now this Murthy had done. Around the same time, Levinson also had done, and then later another person who is very famous now is J.N. Reddy. He also used the same displacement formulation. And then these people have tried to do some machination in order to reduce the parameters that go into this. They have satisfied the top and bottom free surface conditions in order to reduce the number of parameters. But in the process, they have made the theory C1 continuous. So these formulations are not good for finite element formulation, let me tell you. And plus, this does not have transverse normal deformation energy. So thickness deformation is not included. So like this, there are so many people now are in this game. So not only these three, so it became very hot topic. It became, without my realizing, it became a very hot topic later, because nobody knew that composites will come in such a big way. And composites and finite element, because there was also another technique which was parallelly available now for solution. So finite element also developed, composites also developed. So this is the list of papers that started coming. And so Reisner, you'll find he's present in most of the, is a very prolific writer, Reisner. Then our paper is there. Then my students started contributing, and it continued. And so now we are in a situation that, yes, this is before deformation state of affairs. This is with the first set of assumptions that was given in Timoshenko's book, without shear deformation. This is with shear deformation. And this is also with shear and normal deformation. So now we can, and then the dimension of the problem has been reduced to 2 only for plates or shells, and 1 in the case of beams. This slide I would like to show you, because this was with one of my students in 1988. This is the first of its kind, because this we solved it 3-dimensional solution of this plate, 090 cross ply square under sinusoidal loading, and we solved it exactly. We solved it using classical theory. We solved it using Reisner theory, and we also solved it using our higher order. There are so many, higher order theory, and plus, so this is, now you find this when it comes to prediction of stresses, these are all non-dimensional. So this does not, this is A by H. That means as you go from thick to thin, and here sigma x. So classical gives you a straight line. It does not matter. Now, first order, Reisner gives you this pattern, and exact solution gives this path, top one. This is the path. And then we found, surprisingly, that our higher order also follows the same path as the exact. So that means with the 2-dimensional theory, we were able to predict the 3-dimensional behavior. So 3-dimensional behavior were very much, almost exactly represented by a 2-dimensional theory. So this is the great achievement that we found in that year. So situation now is that we can get good deformation, good in plane stresses, good natural frequencies, and we can also solve with okay, thank you. But then there are some limitations. I will just take 5 minutes and then stop. And there are some limitations when it comes to the, because these layered material, they delaminate under action of loading. Sometimes because of the glue is not very good or something has not been done processed properly, so there will be delamination. The split will occur in some portion. Now, why does it occur? I mean, there are so many things. So our assertion was that if you can get a three-dimensional, state of stress that exists at the interface stresses between bottom layer and top layer, if I can estimate these stresses correctly, as if nothing has happened, as if both are in contact, then I can use a material which can withstand that stress and make it safer. Now, this had not been done. The evaluation of transverse stresses in the laminates had not been done even until very recently. People had, the global analysis was done. So this is a unknown problem. So this is what I was telling you. Yes, this that exists, this stresses that exist between the layers, between the top and bottom layer here. These are the stresses. If we can predict these reliably in advance, then I can use a proper material for the gluing, for joining them, so that delamination doesn't take place. So this was there, and we have tried to develop a method that very well. So this is the interface, and so that is our recent work. And this must be, it cannot be done in a simple way. This is how to evaluate. It is called interlaminar transverse stresses. between the two laminas, whatever stresses exist, can we estimate them reliably? So this was a big challenge, and this we have tried to do with another method, which we have developed, a discrete. So normally for three-dimensional equation, we have what is called, there are governing equations. So these are the stress governing equations, which we know. Then we try to integrate this and try to do it layer by layer. That doesn't give you proper solution, because we are still using the two by these sigma x, sigma y, etc. from the two. So we found that yes, we have to start a new approach, a method which is free from any problem. And what we did, we started from three-dimensional. We have made use of all the basic equations of elasticity and presented them into, so we have divided this. I mean, this is the, let us say this is a three-dimensional body. And so what we have done, yes, this, that we have used finite elements in the plane. These are all finite element, these are finite element. And then at each node, so once you do discretization in the plane, in XY plane, and Z dimension, we have left it intact. So obviously, once you have discretized in XY, you will get ordinary differential equation. So from PDE, we have got the equations which is ODE at each of these nodes, which are finite element nodes. And then we have tried to integrate at all these nodes in order to, because numerical integration is much better process than differentiation. Okay, numerical integration always gives you less of error. And this method has turned out to be very good and very reliable. And we have got proof. And so this we have, so this is a, introducing what is called concept of partial discretization. It was already there, this concept for dynamic problem. If you have a space and time problem, you discretize the space, leave time intact, and go in time. So take ordinary differential equation in time. Now what we are doing, if you have a three-dimensional problem, discretize two dimension and leave one out. And we have found that with the use of finite element, we will get a very standard type of equation that we need to solve. And that is this. We will always get a equation of this type, which is, and these are all modular. All these matrices A, B, and P, they are all can be found out from the element properties of the finite element. And then I can integrate this in Z dimension. So this is the standard semi-discrete. So we call it for equilibrium problem, what is discretization, just like we have for dynamic problem, cx double dot plus mx double dot plus cx dot plus kx equal to ft. Now we can say that yes, this is the form that we will get for a static problem. If we can keep one dimension intact, any one dimension in which you are interested, so that can be kept intact, and then we can discretize the others. So the form will always come like this, and which can be integrated. And this way we got the values of these stresses. So after addition, after all this, we get a standard form. So this is a very standard form that we got it. And so this is called semi-discrete. And here we have compared our results. We have found that results are very good. And number of papers have come. But again, the problem is citation. Very few people are citing, and especially from the Western world. If it had been somewhere in some corner of the Western world, people would have jumped on it. But now we are, because it has come from India, it is not being looked at. This is the status. But we feel that, yes, I think it is a good method, and it must be. So different class of problems have been solved, functioning graded, sandwiches, everything has been solved. And we have shown this. So I was telling you about the people who are there in this field. See, J.N. Reddy is a very famous man in College Station, University of Texas. He is retired now. He has written, he is another modern day Timoshenko. He has again rewritten all the books of Timoshenko, plus finite element. So very productive. Another person who is there in this area is Ramesh Batra. Third person is, of course, Carrera. I will not call him because he is like a factory. He's having a factory. He has a paper every week, one paper from his group. He has 25 students around him in Italy sitting there, and something comes, So I will not call him a. But then this Matsunaga, he is from Japan, a single man who works quietly, and he's from a architecture department. He is a faculty member of architecture and single author papers. Very interesting. He works in this area. So, and I mean, you can include me also as in this list. So I'm also there from here. So these 5 people are there in this area, if you call it. And we are trying to do whatever little, but anyway, I'm now 75 plus, so okay, so I will, but most important thing is that this method, which I have told you, this method is a standard form of semi-discrete equation for any equilibrium problem, is this. Just like we got when the finite element developed, that k into d equal to f. How did it come? A standard form. Any problem that you discretize, you will get kd equal to f. So same thing I will say any three-dimensional problem, two-dimensional problem, you discretize, keep one dimension intact, other dimension, if you discretize, you will always get this form. And this form, the advantage is this, all these matrices can be found out from the element properties. They are all element properties. So they are very easily found out, and we can solve so it is general. So all, complicated geometry problem can be solved very easily with free condition. So this has come as a byproduct. And so I would like to thank you. I think it is 4:35, so I must stop. I think I have talked enough. So thank you very much, and thank you very much for giving me this floor to say something. I hope it will help someone, especially the students. I do not know whether they are attending or not, but then, yes. So thank you.
Okay, thank you very much, Professor Tarun Kant, taking all of us through the evolution of micromechanics of laminated composites. It was really a wonderful journey, and also highlighting some of the issues in science and technology in India. I would request the audience sitting here to discuss with you on some of the points that they would like to. But I have one quick comment regarding one of the problems that you have mentioned solved in ISC Bangalore of 3D elasticity solutions. Shouldn't our pursuit be towards the 3D elastic solutions or 3D solutions, 3D elasticity solutions, rather than going for some approximation either in the form of 2D or even the numerical approach of finite element?
So this is the $1,000,000 question. See, 3D problem as such, we have to solve three-dimensional partial differential equation. And 3D partial different PDEs are not easy to solve analytically. So this is also true. And that is why we can solve such problems only for very specified, simple geometry, simple boundary conditions. So yes, some standard problems, some benchmark problems have been solved, but the moment you generalize or you make it little complex loading, no, I cannot get analytical solution. So either you do numerically, that is what my Zinkiewicz told me, who uses plate theory these days? You can use, brute force method of brick element, fill the brick element in your plate or whatever you want, and then get the solution, numerical solution. But mind it, numerical solution is approximate solution. It is not an exact, but analytical solution is exact solution to the extent possible without any analytical solution. So with the inherent, so whether it is plate, if you are getting analytical solution of a plate, it has inherent approximation. So analytical as far as solution is exact, but there are inherent assumptions which have gone into the formulation. So if you are attacking three-dimensional as such and get a solution, yes, that is free from any error, free from any. But then that could be done only for simple problem. So it cannot be. So therefore, our stress is, can we develop a two-dimensional theory without making any assumption? So that is what we have done in higher order theory. In higher order models, we have developed theories without discarding all the assumptions that have gone into Poisson-Kirchhoff theory, Reisner-Mindlin. So we are discarding all those. We are not making any assumption, but still the theory is a two-dimension. And we have found that this two-dimensional is giving as good result as the three-dimension. So you have reduced one dimension. Of course, there is analytical work involved, but you have reduced the dimension, and a two-dimensional problem is easier than attacking a directly three-dimensional problem. That is what is the challenge.
Okay. Thank you. We also have one mechanical engineer with us, Professor Mahajan. So I would request him to raise some points of discussion if he may.
Can these classical theories be extended to things like damage or this thing, or is it?
These are, there are so many people who are working in failure theories because they need the stress values. In any failure theory, you need the stress. set of stress. Stress means stress, a set of stresses, at any point. So if you can reliably evaluate these stresses, reliably, the stress value that we get out of any theory may not be reliable. So it must be reliable. So reliable you have to see. So we find that with the even two-dimensional higher order theories, the stress values are much more reliable. Therefore, use those for your failure theories. So psi and psi theory and this theory, I think there we can use these to predict the failure. So prediction will be better.
But supposing now we find failure at a point due to these failure theories, and the plate continues to be loaded because that failure is only at a particular point. Can we then extend the solutions for the?
No, see. First of all, this is a continuum solution that we are trying to get. So first, the failure will be predicted. Yes, here the stress levels have been exceeded, and therefore this is the point from where now it is going to fail. But it will not remain only at that particular. It will propagate. Once failure is start at one place, and if you go on loading the system further, so it will propagate. So propagation of failure is another study that we can.
Okay, thank you, Professor Mahajan. Though we would like to have more questions, but due to paucity of time, we are going ahead with the event. Now I hand it over to Professor Shantanu.
Yeah, thank you. And thank you, Professor Tarun Kant, for a wonderful lecture. I think it was almost for us sitting in a classroom and understanding the whole big picture getting related. So it's extremely nice. Thank you. So I think there's a presentation of the Prakash medal from INSA. So would you like to say something about the medal, and then we can do the presentation?
I am truly honored and privileged to hand over this award to Professor Tarun Kant. But I have not opened this box yet, but I read the citations. But for me, the citation, I had gone through the citation, but I will read it once more for the audience. And then I will open it and I will hand it over to you. So the citation reads, Professor Prakash Memorial Medal was established in 1987 from an endowment made to commemorate the memory of Professor Prakash, an eminent fellow of the Academy. The medal is awarded once in 3 years to a scientist or an engineer who has made outstanding contributions in any area of engineering and technology. Notably, the first award was given in 1989. But when I saw the list, I found that actually in 89, the award, nobody was awarded this medal. The medal for the year 2019, as we gathered here, is awarded to Professor Tarun Kant, Fellow of National Academy, INSA Senior Scientist and Professor Emeritus, Department of Civil Engineering, IIT Bombay, for his significant contributions to the mechanics of fiber reinforced plastic composites, which has led to better understanding of their behavior. Professor Kant's research interest is in the area of computational methods of structural analysis and theories of plates and shells. His work on thick shell theories and development of numerical integration technique involving segmentation, which could capture boundary layer effects, was significant. Later, he got interested in the field of mechanics of multi-layered fiber reinforced polymer composites. A laminate is a multi-layered composite made up of several individual layers or laminae. Development of 2D accurate beam plates or shell analytical models for these physically 3D laminates has been an area of his active research. He initiated a systematic research effort towards the development of both continuum and discrete finite element, higher order deformation models for improved response characteristics of the laminates in the form of beams, plates, and shells. His demonstration of finite element formulation of higher order displacement theories is considered as a pioneering work and is now being extensively used. His group has clearly demonstrated the application of these analytical and computational models to a variety of problems in structural engineering. Professor Kant is responsible for establishing an interdisciplinary research center for computational engineering and science, that is CCES at IIT Bombay. Professor Kant is an elected fellow of all the academies. He was president of the Indian Society of Theoretical and Applied Mechanics for 2 terms, 1999 and 2000, and has founded Indian Association of Computational Mechanics and Indian Association for Structural Engineering, that is IASC. He is the recipient of 2011 Lifetime Achievement Award of IIT Bombay, besides many others. Professor Tarun Kant was elected to the Fellowship of the INSA in 2007 and is presently its council member 2020 to 2022. Now I would like to open this box if you permit me and then hand over to you.